Hello, calculus students. I hope you're doing well. Now we are well into chapter 4, and this lesson is on section 4.3. Section 4.3 is called partial derivatives. All right, so this is something unique to calculus 3. I want you to look at this background. You saw this before, and you see this point here. This yellow surface is a graph of a function f of x, y. And do you see this point here where the blue vertical line ends? This represents the origin, okay? Now the question here is this function moving up, like going up, increasing, or decreasing at that point, right? And I think you can clearly see that this is not a good question because the question depends, the answer depends on which direction you are going, right? If you're going in a certain direction, then the z-value or the level at which you are at is increasing, and maybe in other directions it may be decreasing. So that's different from what you saw in calculus 1. Anyway, we will be able to address questions like that after you study section 4.3 and then 4.4. Okay, so these are two crucial sections. Let's get started on section 4.3. Section 4.3, partial derivatives. All right, so what do we do? How do we always start a new section of calculus 3? You're right, we always start from with something you already knew from calculus 1, okay? All right, so this is calculus 1. First, we talk about this function. This is what you learn in calculus 1. What we're, of course, studying now is calculus 3, but it's based on this concept of calculus 1, which is actually based on probably one of the first things you learned in your high school or junior high or elementary or kindergarten algebra class. The idea of a slope. What is the slope of a line, right? The slope, typically called m, for some unknown reason. Some people say it's the beginning letter of the word slope in French. I am not quite sure. That sounds like a reasonable guess, right? But a slope, what is slope? M. This is the rise over run, right? And so the delta x, y over delta x, it's called the rise over run. Actually, here, let me just go ahead and do this. If the line is a straight line, okay, so this is fine. This is how we define this, rise over run. If a f is linear, okay? And so it's y1 minus y2 divided by x1 minus x2, whatever. We have different formulas for that. Okay, so, but if you try to make this h smaller and smaller, in other words, you take the second point and make it closer and closer to a, basically from both directions, that's the idea of the limit, right? So that is the definition of the derivative. The derivative is defined actually in this way. You can also write this as delta y over delta x, but it's a limit as delta x approaches 0. Now, normally in a calculus class, this is what you learn. It's a limit at h approaches 0 of f of x plus h. That's the second x number here, right? I wrote a here, but this is true for an arbitrary point x, minus f of x all over h. Okay, and because h is delta x. Of course, you write this as y prime or dy over dx. Basically, when the delta changes into the English letter d, we are taking an infinitesimal step to get this thing here. And of course, you know this as the instantaneous rate of change of the function f or y with respect to x. And I'm going to spell this out. Okay, because what we are saying is, let's say the rate of change is 5, okay? What we are saying is, right at this point, okay, if f prime of a is 5, what we are saying is, right at this point where x is equal to a, the rate of change is 5. And what that means is, this will be increasing at the rate of 5 units as x increases by 1, okay? That's the whole idea. So we say with respect to x. It's the rate of change of f of x or y with respect to x. Now, normally you don't have to say this because x is the only variable. And see, now you can see why this has to be changed a little bit, right, in Calculus 3, because now the picture looks more like this. Calculus 3, in chapter 4, we are talking about multivariable functions. So if f depends on x and y, let's say here we have a point in the domain of f, which is AB, and the value of the function is, of course, the z value of this point, right, on the surface representing f of x, y. So here is the definition. And by the way, I am going to define the derivative, but a derivative, maybe two derivatives at this point. How do you describe the rate of change? Okay, as I mentioned at the beginning of this video, where, if you are standing, let's say you are standing on this surface, which is f of x. If you're standing right here, or if you're sitting right here, are you going to increase or decrease? Okay. Well, see, the thing is, in Calculus 1, we only had one dimension in the domain, the x-axis, right? So we can assume that as x increases, what would y do? So if the derivative is positive, that means the function is increasing at that point. If the derivative is negative, the function is decreasing at that point. Okay, so this wasn't a big problem because you only had one direction. Over here, you have tons of directions, infinitely many directions. Okay, you can go this way or any kinds of ways. So we can't just talk about the rate of change, okay? But we can talk about the rate of change in the direction of, and then we can describe that direction by a vector, okay? But the fundamental to that idea of the directional derivative is this idea of the partial derivatives. Okay, so this is one of the most important things you learn in Calculus 3, probably one of the first distinctively multivariable things in Calculus 3, the partial derivatives of f of x. Okay, what do we mean by this? All right, so I will first define f sub x. You can also write this as dx of f, so this means the derivative of f with respect to x. Sometimes we see and watch this new symbol that we see. This is the partial symbol of f(x), okay? So this is a unique, so it looks like a lowercase d, but it's not. It's more like, the wrong way number 6. But this represents the partial of f with respect to x. And this is the limit as h approaches 0 of, looks familiar so far, right? It's x plus h, comma, y. So y doesn't change, but we add h to x in that direction, minus f of xy divided by h. So what in the world is that? Okay, we're adding h in the x direction. So this is that direction, okay? In other words, what we have just defined is the rate of change in the positive x direction, right? That's what f sub x is. F sub x is not this vector, but f sub x is the rate of change of f if you are to go in the direction of the positive x-axis, all right? And similarly, of course, f sub y is the partial derivative of f with respect to y, which is this f over y, and that is defined as the limit as h approaches 0 of, and you can probably guess this, it's x comma y plus h. This time you go h direction, the h units in the y direction, and then find the difference between the value of the function at the new place minus f of xy, that's the difference in the z coordinates, and then divide it by h. Okay, so what does this mean? Okay, this is the rate of change, of course, but not just a random rate of change, the rate of change in the positive x direction. Okay, and so the key thing here is, notice here, y didn't change, right? If you keep going in this direction, y doesn't change. If you keep going in this direction, the x does not change. So I'm going to write this in red because it's super important. In order to calculate f sub x, think of y as a constant. Y doesn't change. Assume that y doesn't change because you're going in the x direction. F sub x, by the way, this is not a hard concept. Okay, once you practice this a few times, you'll be an expert in taking partial derivatives within minutes. Okay, this is the rate of change of f, of course, in the y direction. And so here, in order to find the partial derivative with respect to y, you just keep x constant, right? And so that's really the key. I mean, what I have just written here summarize pretty much everything you need to know about this section. Okay, so now you can just turn off the video and go home, or you're already at home. No, don't do that, okay? Because I have more important things to say. All right, so what does it mean if this is positive? Okay, if this is positive, that means in the direction of x, the f is increasing. If this is negative, that means it's decreasing, and so on. All right, let me give you an example. F of xy is equal to y sine of x plus e to the, should I try to make this more exciting? Nah, that's okay. E to the y, okay. All right, so for fx, pretend treat y like a constant, okay? Pick your favorite constant, 3 or 17 or 51 or whatever. Treat y like a constant. So here is the answer to this. Fx, which is your partial of f with respect to x. You can use any notation, any of these notation. So if y is a constant, like 5, this will be 5 sine of x, right? Oh, sorry. We have to take the derivative with respect to x. So sine of x becomes cosine of x. So that part is not changing, but y doesn't change, okay? So you don't have to apply the product rule or any kind of rules here. Just pretend like this is 5 sine x, that would become 5 cosine x, right? So because y is like a constant. And guess what? E to the y is also a constant. So that just becomes 0. You see that? Okay, so it may look sort of weird at the beginning, right? But that's how you have to train your brain to think, okay? So for f sub y, what do? Well, yes, treat x like it's 3 or 7 or some kind of constant, okay? So, so then f sub y is equal to, notice here, x is like a constant. So sine of x is a constant. So what happens if this was like 5? 5y becomes 5, right? So the first part just becomes sine of x. You get that? Y sine of x is y times a constant. The derivative of that with respect to y is just that constant. Just like if you take the derivative of 5x, you get 5, right? And then plus, now e to the x is just, e to the y, with respect to, if you take the derivative with respect to y, you just get e to the y, right? You don't get 0 because y is actually here, not x. All right, so that's how you can take the derivatives. These are called partial differentiation. What we have just done is called partial differentiation. It is the process of finding partial derivatives. All right, the second equation or second example, let's say you have y times cosine of xy. That's a little tricky, okay? All right, what's f of f sub x? Okay, so think of y as a constant. So this is a constant multiplier. You can always just keep that. The inside, now you have cosine of, think of y as a constant again. So think of this as cosine of 5x. What is the derivative of cosine of 5x? Well, that's negative sine of 5x multiplied by 5 in the front, right? So it becomes negative y times sine of xy. Okay, did you get that? All right, so this will be negative y squared sine of xy. How do we get this? Well, again, because we are thinking of y like a constant, I'm just going to keep y just in the front, okay? And then cosine of xy becomes negative sine of xy times the derivative of the inside function, but with respect to x, xy becomes y, because this is just like 5x becoming 5, right, with respect to x. Think of y as a constant. So that's how you get that answer. F sub y in this case, this is a little tricky, okay, because you have this times this. Both of them have a y in it. Okay, so guess what? You need the product rule. Okay, the product rule says the derivative, and remember, x is treated like a constant. Anytime you see x, think of 5 or 51 or your favorite number. Okay, so the derivative of the first, that's 1, times the second, plus the first times the derivative of the second. Now we get to take the derivative of cosine of xy with respect to y, thinking of x as a constant. All right, so then you get negative sine of xy times the derivative of the inside function. The inside function is just like 5y becoming 5. So then the 5, or in this case, x, the coefficient comes in like that. So the answer here is cosine of xy minus xy times the sine of xy. Now this, you may think, okay, this is trivial. This is really so easy. I don't need to practice. And maybe so, maybe you don't need to. But I think most of you will probably need some practice. It's not a hard practice. This is, and I guarantee, I mean, if you are able to pass calculus 1 and 2, this is not the most challenging thing you have done. So just with a few practice exercises, you will be able to do this. Okay, so cosine of xy, it's minus xy times, the sine of xy. And so maybe I should, no, it's okay. Maybe I will just go to the next one, right? How about if f is xy cubed, okay? Is it simple? Maybe too simple. What's fx? Yeah, it's y third. No problem here, right? And then how about fy? This is 3xy squared, thinking of x as a constant again, right? So that is what we get. No problem, right? And you will see some other problem. Maybe I should give you another problem here. Okay. In fact, let's go ahead and try this. And this may give you a great exercise here. Plus x squared e to the y. All right, let's see what you can come up with, right, with this. Find fx and find fy here, okay? And then when you do that, you can come back and start the next part of this video.